Hey, grade 12s, we're going to continue on with balancing using oxidation numbers today. And I want to take a look to start at what do we do when we have special situations called ratios and splits. Now, this is a great example of a question involving ratios. And I'll show you what I mean by that. It doesn't matter what we're doing. We're going to follow along with the same set of rules that we learned the other day. We start by assigning all of the oxidation numbers. And you'll see that I've got the pertinent oxidation numbers already up. We can see the manganese goes from +7 down to +2 as the reaction proceeds. And the chlorine is going to go from -1 up to 0 as the reaction proceeds. So in both cases, we've got something being oxidized and something being reduced. Now, for the chlorine to go from -1 up to 0, it has to have lost electrons. And we can see that it's lost 1 electron. And so that's our oxidation. In order for manganese to go from +7 down, that has a gain of electrons. And it's gained 5 electrons per manganese to get down to a charge of +2. And so there's my reduction. So these now need to be made equal. And I can very quickly see that if one chlorine is moving 1 electron, if I multiply it by 5, then 5 chlorines moves 5 electrons, and I only need one of the manganeses to move 5 electrons. That way I've got 5 electrons being gained and 5 being lost. And here's where we run into a problem. It would be easy for me to get 5 chlorines here, but how do I get 5 chlorines on this side? This little number 2 is going to have the unfortunate effect of wanting to double whatever number I put there. If I were to have written the number 5 here, then I'd have 10 chlorines on that side. I'd have twice as many as I needed, and my equation wouldn't balance. So what do? Well, when we have this even-odd scenario, I have a 2 on one side and a 1 on the other, and I'm trying to get to an odd number. Then what I do is, if you can't beat them, join them. If this 2 is going to multiply everything by 2, then we're just going to go ahead and multiply both the top and the bottom both by 2. I'm going to try to get a total of 5 times 2. I'm going to try and get to 10 chlorines, and 1 times 2 is 2 manganeses. We know that if 1 chlorine moves 1 electron, 10 would make 10 electrons. If 1 manganese moves 5 electrons, 2 of them makes 10 electrons. So we're going to go for getting groups of 10 chlorines. I can put a 10 here to get 10 chlorines, and a 5, which is being multiplied by that little subscript, is 10. I'm going to get 2 groups of manganese here and here. And again, what we want to remember is that we're only balancing the redox species. We've got 10 chlorines before and after, 2 manganeses before and after. We're not worried about anybody else at this point. Now we're going to balance the remaining species by inspection. So I can choose to balance either the hydrogens or I can choose to balance the oxygens. In this case, however, I've got a hydrogen here by itself, and I can put any number that I need to in front of that in order for it to balance. So I'm going to recommend we balance the oxygens first. We now have 2 groups of 4 is 8, so we can quickly put an 8 in front of the water to get 8 oxygens. This now gives us a total of 16 hydrogens, and so we can very quickly put a 16 in front of the hydrogen to get 16 hydrogens. This equation is now completely balanced. You have this next one available for you in your books. It'd be my recommendation that you pause the video here, try to solve it on your own, get as far as you can, and then when you're ready, press play and see how you do. All right. You can see that chlorine went from a charge of 0 down to a charge of -1. That was a change of 1 electron, whereas irons went from 0 up to 3. So they lost 3 electrons. The multiplier we use to make the electrons equal we're going to try to turn them both into 3. If one chlorine moves 1 electron, then 3 of them will move 3 electrons. And one iron moves 3 electrons. The electrons in are now equal to electrons out. But here's where the problem was. There was no way to get 3 chlorines because of this little 2 here. We have an even-odd problem. We want an odd number, but we're getting an even one. So we multiply both the bottom and the top by 2. We are going for a total of 3 times 2 is 6 chlorines, and a total of 1 times 2 is 2 of the irons. We now use these as our starting points to balance the reaction. And the balancing works out to be 2, 3, 2. Let's do one more example. Let's take a look at this scenario. We have antimony reacting with nitric acid. First step, try and see if you can solve for all of the oxidation numbers and then draw your connecting line to see who went up and who went down, who gained electrons and who lost them. Pause the video here and see if you can get at least that far. When you're ready, press play. So I've assigned all the oxidation numbers for you. You can see antimony has gone from an oxidation number of 0 up to an oxidation number of +5. It was oxidized. In its process, it was oxidized because it lost 5 electrons. The nitrogen went from +5 down to +2. It was reduced. It was reduced because it gained 3 electrons. We now need to make them equal. The multiplier that will make them equal to each other is we can make these both into 15s. I'm going to multiply this line by 5 and multiply this line by 3. That gives me 15 electrons in both cases. Here's where you're going to have a problem. It's not possible for me to get 3 antimonies on this side because of this number 2. I need an odd number, but the number 2 is making it into an even number. The fix for that is to multiply both the top and the bottom by 2. We'll just double everything. 5 times 2 is a total of 10 antimonies. Or sorry, this is the nitrogens. 5 times 2 is a total of 10 of the nitrogens. And 3 times 2 will give us a total of 6 of the antimonies. So we're going to use those as a starting point for our balancing. I'm going to need totals of 10 nitrogens, so I can put a 10 here and a 10 there to get 10 nitrogens. I'm going to need a total of 3 times 2 is 6 for the antimonies. So I put a 6 in front of this antimony. I only need to put a 3 here because 3 groups of 2 gives me 6. Once my redox species have been balanced, we balance the remaining species by inspection. I have 10 hydrogens before the reaction, a 5 makes 10 hydrogens after, and if you check, you'll find that your oxygens are automatically balanced. This is an example of a split reaction. You'll notice that I started with all the same starting steps. I've assigned my oxidation number. We notice this becomes a split because I find out that the only species whose oxidation number changed was the chlorine. Before the reaction, chlorine in this species is +5, and in this species is -1. After the reaction, chlorine is at a 0. Remember when you draw your connecting lines that they must always go across the arrow. You would never try to connect, for example, these 2 chlorines to each other because there was no reaction where one changed into the other. So my 2 changes in oxidation numbers happened because these chlorines went from -1 up to 0, that's my oxidation, and these chlorines went from +5 down to 0, that's my reduction. This is called a split reaction because both of my connecting lines are pointing to the same species. It's split in terms of some were oxidized and some were reduced. But we treat it the same way. We need to have the total electrons lost be equal to the total electrons gained. So a common factor for 5 and 1 is I can make them both into 5. If I multiply the top line by 5 and the bottom line by 1, then they both have 5 electrons. But what do I do with those numbers? Well, what we say is that one of these chlorines was moving 5 electrons, so I just need one of those chlorines. And 5 of these chlorines were moving 1 electron, so I need 5 of those chlorines. We use these points for the other side of the reaction, not the split. What do I do for the split side, the side that has both been oxidized and reduced? Well, I have a total of 1 and 5 is 6 in total. So to get 6 chlorines on this side in total, I put a 3. My redox species have now been balanced. I have the same amount of chlorines before and after, and I have enough to have the right amount of electrons. I'm now going to balance all my remaining species by inspections. In this case, I've got potassiums, oxygens, and hydrogens to balance. I'm going to choose to start by balancing the potassiums first because they already have coefficients on my reactant side. I've got a total of 6 of them, so I need 6 on my product side. And then I balance the remaining oxygens and hydrogens with a coefficient. We'll do one more example and get you guys to try this one. So start by trying to assign all your oxidation numbers, draw your connecting lines to your redox species. Pause the video here, try it for as far as you can get on your own, and when you're ready, press play and we'll work through it together. You'll notice that the only species whose oxidation number changed was bromine. Bromine went from 0 before the reaction, +5 in this case, and -1 in this case. Remember, when you draw your connecting lines, make sure that you cross that central reaction arrow. You're not connecting these two species to each other. They did not react with each other. These first bromines reacted to form sodium bromate and sodium bromide. Bromine went from 0 up to 5, that's a loss of 5 electrons. That was your oxidation. And here from 0 down to -1 was a gain of 1 electron. That's your reduction. We're going to start by making these both into a total of 5. So we have 5 electrons in, 5 electrons out. Now remember, when both of my connecting lines point at the same species, I cannot use these numbers for that species. I use them for the other side of the reaction. I'm going to need 1 of these bromines, and I am going to need 5 of these bromines. So we start there. We now have a total of 1 plus 5 is 6 bromines. So to get 6 bromines on the reactant side, we put a 3. These are groups 2. So we now have 6 bromines. Now we'll choose to balance the sodiums because on the product side, we already have coefficients that we use for balancing the bromine, and they cannot change. There's a total of 6 sodiums there, so a 6 makes 6 sodiums on the other side. And finally, balancing the hydrogens. To get 6 hydrogens, we can put a 3 here, and our reaction is balanced. In your workbook, you guys have several more questions to do on those pages labeled simple ratios and splits. There's also a few questions you can do out of your textbook, and we're going to get you guys practicing that for the next day or so, and then I'm going to teach you one more way of balancing using redox numbers and oxidation numbers, and that's an acid and basic solution. But we're going to get this done first. All right, thanks so much. We will get to you with our next lesson soon.